All right, so some people have questioned how do you determine the location of the subsolar point? The subsolar point is the location where the sun strikes the surface of the planet at a 90-degree angle, a direct angle. Sub underneath the sun, a direct angle of 90 degrees. The sun's rays come in and hit the surface at a 90-degree angle. So we're looking for the location of the subsolar plane. Now, let's pretend that we have the sun out here, right? So there's this object that's emitting a lot of energy, a lot of light, and it's coming out and it's striking this mysterious surface in the middle of space. If the Earth were flat, the sun would strike the surface at 90 degrees every single place on the Earth. But it doesn't because the Earth isn't flat. Let's go ahead and erase this and take a look at the Earth and the sun in space. Now remember, the Earth travels around the sun. Here's our Earth, here's our sun, not drawn to scale. The Earth travels around the sun in an orbit that is not a circle. It's elliptical. Sometimes the Earth is physically farther from the sun. At other times it is physically closer to the sun. Perihelion, peri, close. Helion, sun, close to the sun. Aphelion, ap, far. Helion, sun, farthest from the sun. All right, so as the Earth is revolving around the sun, 365.25 days, it is sometimes physically closer and sometimes physically farther. There is one more really important relationship between the Earth and the sun in space that is going to account for the migration of the subsolar point. That is the fact that the Earth is tilted 23.5 degrees on its axis with respect to a line that is drawn perpendicular to the plane of the ecliptic. Plane of the ecliptic is a fancy way to say orbit. The orbit that the Earth has around the sun. Remember, it's an ellipse, it's not a circle as it goes around the sun. So let's have this line be the plane of the ecliptic. We're going to now draw our Earth and a line that intersects the plane of the ecliptic perpendicular or 90 degrees. The red line here is going to represent the equator of the Earth. The North Pole, the South Pole, and the line that goes through the center and connects those is called the axis. Notice that I did not draw that axis line to be the same line that I drew that was perpendicular to our plane of the ecliptic. Why? Because the Earth's axis is tilted off that line by 23.5 degrees. We're measuring that angle, that line that's drawn perpendicular to the plane of the ecliptic, and the axis. We're measuring the angle between those two. That's 23.5 degrees. The Earth is tilted. It has an axial tilt of 23.5 degrees. And it maintains that axial tilt as it revolves around the sun, as it rotates, spins on its axis, and revolves around the sun. That consistent positioning of the North Pole with respect to outer space is termed parallelism. If I were to stop the Earth's movements over and over and over again and draw imaginary space lines, they would all be parallel to each other because it's always consistently tilted. Now, over the really, really long term, thousands of years, that does adjust a little bit. But in our lifespan, it's not going to change. So now let's redraw our orbit of our Earth. Here's our plane of the ecliptic. Sun is in the center. The sun isn't moving with respect to the Earth, but the Earth is moving with respect to the sun. Remember, our Earth is tilted. It's not perpendicular. It's tilted. So this is capturing snapshots of the Earth in its orbit as it goes around the sun over the course of the year. Also remembering, sometimes it is physically, the center of the planet is physically closer to the center of the sun. Sometimes that's farther. Perihelion, physically the closest point. Aphelion, physically the farthest point. Perihelion occurs in January. Aphelion in July. So physical distance from the sun has very little impact on our weather patterns, on our seasons, on the air temperature. Because in the northern hemisphere here, we experience our physically closest point to the sun when we are on average coldest. And the opposite, when we are on average warmest, we are actually physically farthest from the sun. What's driving this change is the axial tilt. As the Earth is revolving around the sun, parts of the planet are tilted towards the sun, and parts of the planet are tilted away from the sun. And when you're tilted towards the sun, you get a higher angle of sunshine. Remember, sunshine coming in, striking a surface. 90 degrees is the maximum angle, the subsolar point. When you are getting 90-degree angle sunshine, the subsolar point, you have the greatest concentration of energy that is possible. That results in the warmest air temperatures. When you have less than 90 degrees, you're sharing some of that energy with other spaces. Remember, the sun is giving off, reasonably so, the same amount of energy every single moment of every single day, and it's going off in all directions because the sun is a sphere, so it's going off in all directions in outer space. It's not changing really the output of energy, but that energy travels through space and hits surfaces, and the angle at which it hits the surface dictates how far of an area we have to spread that energy out. Try this at home. Take a flashlight, go over to a dark wall, and make sure that you're shining the flashlight such that the light hits the wall directly on, just like it is right here in this image. That's 90-degree angle. Now, begin to rotate your flashlight so that you're changing the angle. The amount of light that's coming out of your flashlight is not going to change. But the area of the wall that light is having to hit is going to get bigger or smaller depending upon the angle at which it hits. You're consistently giving off the same amount of energy, but you're making larger or smaller areas share that energy. And because the subsolar point is going to migrate, move up and down over the surface of the Earth because the Earth itself is moving, so the sun's not moving. The solar energy is coming out in all directions, consistently. But because the Earth is tilted, its relative position is changing as it moves around the sun. So the angle will change, and hence the location of the subsolar point will move. The subsolar point will migrate over the course of a year between two locations on the surface of the planet. Here's our planet again. Our equator here, dividing it into the northern hemisphere and the southern hemisphere, North Pole up here, South Pole down here, notice. 23.5-degree tilt. I know that's barely readable, but 23.5-degree tilt. We have a line here and a line here, 23.5 degrees north, 23.5 degrees south. At the very beginning of class, I asked you to memorize the numbers and names of these lines. This is the Tropic of Cancer. This is the Tropic of Capricorn. The subsolar point will migrate over the course of the year between those two lines. It will hit the Tropic of Cancer on the summer solstice in the northern hemisphere, or what we call the June solstice. Typically, that's June 21st. It will hit the Tropic of Capricorn on the December solstice. That is typically December 21st. On June 21st, the northern hemisphere will have its longest day, its highest angle of sunshine. Where will the angle be 90 degrees? Right here at the Tropic of Cancer. Everywhere else, less than 90. 90 degrees There and only there, because the subsolar point is only one spot on the planet at any given time. So June 21st, Tropic of Cancer, 90 degrees, subsolar point. Everywhere else on the planet that's getting sunshine will have less than a 90-degree angle. Some places won't even get sunshine. On December 21st, when the subsolar point is down here at the Tropic of Capricorn in the southern hemisphere, the reverse is true. Now, the Tropic of Capricorn will have 90-degree sunshine, the subsolar point. Everywhere else on the planet, less than 90 degrees. And as the subsolar point migrates between those two, moving up, and then down, and then up, and then down, and then up, and then down, and then up, and then down, we can track that angle of incoming sunshine, that angle of insolation, incoming solar radiation, insolation. It will never be more northern than 23.5 degrees north. And it will never be more southern than 23.5 degrees south. So if I have a latitude of 40 degrees north, and I ask you how many times will the subsolar point hit 40 degrees north, the answer is 0. The subsolar point will never hit 40 degrees north because its maximum extent in the northern hemisphere is the Tropic of Cancer. If I asked you, how many times will the subsolar point hit 51 degrees south, the answer is 0, because it will never go further south than the Tropic of Capricorn, which is 23.5 degrees south. How many times will it hit the Tropic of Cancer in a year? Well, once, only on June 21st. How many times will it hit the Tropic of Capricorn? Only once, December 21st. Everywhere in between, twice. Once, down again a second time, up, down, up, down, up, down, up, down. As it migrates, because the Earth is tilted. As it spins on its axis and revolves around the sun, different parts of the planet are getting different angles of sunshine. Now, it's really important. And if I were in a classroom, I would take a globe and we'd hold flashlights out and we'd watch this. The Earth does not do this. It does not wobble up and down. It doesn't bounce. It maintains as it moves. But because of the tilt, sometimes the southern hemisphere is tilted towards the sun, and sometimes it's the northern hemisphere. I hope that helps.